How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're on a flight, cruising at 35,000 feet. The world outside the tiny oval window is a serene canvas of white clouds and deep blue. Inside, you're in your own little bubble, disconnected. The Wi-Fi is either prohibitively expensive or simply not working. You are, for all intents and purposes, an island. You decide to pass the time by cleaning up your phone's photo library. You come across a great picture from a recent trip, a beautiful shot of a landmark, almost perfect, except for the tourist in the bright yellow jacket standing right in the frame, completely ruining the composition. You tap Edit, circle the offending figure with your finger, and tap a button that says something like Magic Eraser or Object Removal. And then it happens. In less than a second, with no loading bar, no connection to the internet, the tourist vanishes. Not just smudged out, but gone. The phone has intelligently filled in the background behind him. The cobblestones, the edge of a fountain, the shadow of a nearby building, as if he was never there. The photo is perfect. You sit back, a little stunned. It feels like a minor miracle, a piece of digital wizardry performed in a metal tube hurtling through the stratosphere. We've all had these moments. Maybe it wasn't a photo. Maybe you were typing a text message, and your phone suggested not just the next word, but the entire rest of your sentence, perfectly capturing the tone and context of your conversation. Or perhaps you pointed your camera at a menu in a language you don't speak, and instantly, right there on your screen, the words transformed into your native tongue. These are small sparks of magic that we encounter every day. And our assumption, if we think about it at all, is usually the same. This must be coming from the cloud. We have a mental model of how AI works. We imagine our little device, our phone or our laptop, as a terminal, a sleek glass and metal window into a vast, powerful intelligence that lives somewhere far away. We picture massive data centers, rows upon rows of humming servers in a nondescript building in Oregon or Virginia, owned by Google or Apple or Microsoft. When we ask a question, our device sends a signal to this giant, centralized brain. The brain does its thinking, and then it sends the answer back. It's a canned response. And for many of the most impressive AI feats we see, that model is absolutely correct. But then comes the record scratch moment. You're on an airplane. You're in airplane mode. There is no signal to send, no giant brain to call upon. Yet the magic still happened. The intelligence wasn't out there, somewhere in the cloud. It was right there with you, inside that small, cool device resting in your hand. So where did it come from? How is it possible to fit a thinking machine, something capable of understanding images and language, into a pocket-sized computer powered by a battery? This is the story of a silent revolution in artificial intelligence. It's not about the behemoth models that dominate the headlines, the ones that can write novels or create photorealistic art. It's about their smaller, more modest, and arguably more integrated cousins. Today, on First Principles, we are opening the black box of on-device AI. We're going to deconstruct the magic of the thinking machine in your pocket and discover the fundamental ideas that allow a sliver of silicon to behave as if it has a mind of its own. We're going to talk about micro large language models. The magic we see on our devices is defined by its intimacy and its immediacy. It's a different flavor of intelligence from what we experience when we use a web-based chatbot. That experience, while incredible, often has a slight but perceptible latency. You type your query, press enter, and for a moment, you can almost feel the digital gears turning continents away. There's a slight pause as your request travels through undersea cables, gets processed by a warehouse full of computers, and the response makes the long journey back to your screen. On-device AI is different. It's instantaneous. When your keyboard suggests the perfect witty comeback, it appears as you type. When your voice assistant transcribes your spoken words into text, the letters appear on the screen in near-perfect sync with your voice, even if you're in a subway tunnel deep underground. This immediacy changes our relationship with the technology. It doesn't feel like we're using a service. It feels like the device itself understands us. The intelligence is woven into the fabric of the operating system, a constant, helpful presence. And then there's the profound implication of privacy. In an era where data has become the world's most valuable commodity, the idea of our personal information being sent to a remote server for processing can be unsettling. Every photo we upload, every message we send, every voice command we issue to a cloud-based AI is a piece of ourselves that we are handing over. But with on-device AI, the computation happens locally. The photo you're editing never leaves your phone. The conversation your messaging app is analyzing stays on your device. The voice memo you're transcribing is processed right there. This creates a powerful sense of security. The magic is happening in your digital home, not in a stranger's house. Think of the real-world applications this unlocks. Smart cameras that can identify people, pets, and objects in real time to give you more meaningful notifications. Live translation apps that allow two people speaking different languages to have a fluid conversation without an awkward, delayed, cloud-based intermediary. Accessibility features that can describe a scene to a visually impaired user. All done instantly and privately. These aren't futuristic dreams. They are features available right now on the devices many of us carry. They are so well integrated, so seamless, that we often fail to see them for the technological marvels they truly are. They work so well that they become invisible. And that invisibility is the hallmark of their success. But it also hides the fascinating story of how they came to be. To truly understand why on-device AI is such a breakthrough, we have to rewind the clock just a few years to the dawn of the modern AI boom. Around the early 2020s, the world was captivated by the emergence of truly massive language models. Like OpenAI's EP33, these models were, and are, monumental achievements of engineering. They were trained on unfathomably large datasets, a significant portion of the entire internet, and consisted of hundreds of billions of parameters. A parameter, in this context, is essentially a tunable knob within the neural network, a value that gets adjusted during training. The more parameters, the more capacity the model has to learn complex patterns and nuances in data. These models were giants in every sense of the word. They lived in sprawling, custom-built data centers, requiring immense and continuous power, sophisticated cooling systems, and an army of specialized, expensive computer chips to run. The cost of training one of these flagship models ran into the tens, and eventually, hundreds of millions of dollars. They were the digital equivalent of building a pyramid or a cathedral, a monumental undertaking that required the resources of a technological empire. And this created a fundamental problem. The very thing that made these models so powerful, their colossal size, also became their cage. They were tethered to the data center, the dream of ambient computing, of an intelligence that could be embedded in every object around us, was running headfirst into the wall of physical reality. You simply cannot put a power-hungry, city-block-sized data center into a smartphone. You can't put it in a car's dashboard, or a smart speaker, or a medical device. The cloud was an incredible solution for many things, but it couldn't be the answer for everything. The lag, the reliance on a constant internet connection, the privacy concerns, and the sheer energy consumption made it impractical for a whole class of problems that demanded speed, efficiency, and autonomy. This was the high-stakes question that researchers at the world's leading tech companies and universities began to grapple with. The question was no longer just, how can we make these models bigger and more powerful? A new, more subtle question emerged. How can we make them smaller and smarter? How do you take the distilled wisdom learned by a digital behemoth and decant it into a vessel that can fit in your pocket? How do you capture the essence of that intelligence without the crippling cost of its physical form? The challenge wasn't to build a bigger brain, it was to design a more efficient one. They weren't just trying to scale up, they were trying to scale down, elegantly and intelligently. The solution would not come from brute force, but from ingenuity. So, let's open the box. When we think about making something smaller, our intuition often leads us to a simple, subtractive process. If you have a large block of clay and you want a smaller statue, you chip away the excess. If you have a long essay and you want a shorter summary, you delete paragraphs. A common misconception about micro LLMs is that they are created in a similar way, that developers take a massive model like GPT-4 and just chop it up, delete half the layers, remove a few billion parameters, and voila, you have a light version. But this approach doesn't really work. A large neural network is an incredibly complex, interconnected system. Its knowledge isn't stored neatly in one section, like a chapter in a book. It's distributed across its entire structure. Simply hacking parts off is more like performing a lobotomy than creating a more efficient brain. You'd be left with a damaged, incoherent system that has lost the very capabilities you were trying to preserve. The real process is far more sophisticated, more artful. It's less like demolition and more like horticulture. To understand it, we need a core analogy. Imagine a world-renowned master chef. Let's call him Chef Antoine. Antoine has dedicated his life to the culinary arts. He has trained in every major culinary tradition, memorized every classic recipe, and understands the chemical interactions of ingredients at a molecular level. His personal library of cookbooks, notes, and techniques fills a warehouse. This is our massive cloud-based AI model. Chef Antoine can, given any prompt, create a breathtakingly original and flawless dish. But he comes with some significant constraints. He requires a massive, state-of-the-art industrial kitchen, a full brigade of sous chefs, and an astronomical budget. You can't hire Chef Antoine to help you with your Tuesday night dinner. He is, for all practical purposes, inaccessible for everyday tasks. Now, imagine you are a publisher of cookbooks for home cooks. Your goal is not to replicate Chef Antoine in his entirety. Your goal is to create a small, elegant, and highly practical recipe book that captures the essence of his genius, but is designed for a standard home kitchen with basic equipment. This recipe book is our Micro LLM. How would you create it? You wouldn't just go into his warehouse-sized library and randomly tear out pages. That would result in a chaotic, unusable mess. No, the logical approach would be to have the master himself, Chef Antoine, create the book. You would ask him to distill his vast knowledge into a new, compact form. He would draw upon his deep understanding to create simplified, efficient recipes that deliver 90% of the flavor for 1% of the effort. He would know which exotic, hard-to-find ingredients could be swapped for common ones, which complex, multi-day processes could be simplified into a few key steps, and which culinary rules could be bent or broken without ruining the final dish. The resulting book wouldn't be a damaged version of his giant library. It would be a new, purpose-built creation, a masterpiece of efficient wisdom. This process, This act of a large expert system teaching a smaller, simpler one is the first and most fundamental principle behind creating micro LLMs. This core principle has a name: knowledge distillation. It's a beautiful and intuitive idea. Instead of training a small model from scratch on a raw dataset, which can be difficult and time-consuming, you use a large, pre-trained teacher model like our Chef Antoine to guide the training of a smaller student model, our home cookbook. The teacher model does something remarkable. It doesn't just provide the student with the correct answers, it teaches the student its thought process. Let's move from the kitchen to a more direct example. Imagine you're training a small model to perform sentiment analysis, to read a sentence and decide if it's positive, negative, or neutral. A simple training method would be to feed the student model a sentence like, "I love this movie," and tell it the correct label is positive. This is called using hard labels. The answer is either right or wrong. But the teacher model does something much richer. It provides soft labels. For the sentence, "I love this movie," the teacher model might say, "My analysis indicates that I am 98% certain this is a positive statement, 1.5% certain it's neutral, and 0.5% certain it's negative." This extra information is incredibly valuable. It's the model's way of expressing its confidence and its uncertainty. It's revealing the nuances of its prediction. It's telling the student model how it thinks. It's teaching the student not just the what, but the why. By learning from this richer, more nuanced guidance, the student model can learn the complex patterns and generalizations of its powerful teacher much more efficiently than it could from raw data alone. It's a way of transferring the intuition of the massive model into its smaller protege. This is Chef Antoine, not just handing over a recipe, but explaining the theory behind it. Why you sear the meat to create a flavorful crust, why a dash of acid brightens a rich sauce. So, through knowledge distillation, we have our student model, our compact recipe book. It's already much smaller and more efficient than the teacher. But the quest for efficiency doesn't stop there. The next step is to make it even more compact, to shed every last bit of unnecessary weight. This brings us to our second principle, pruning. If knowledge distillation is about writing the book, pruning is about the ruthless final edit. Imagine our newly created recipe book is still a bit wordy. An expert editor goes through it, page by page, looking for redundancies. The recipe might say, "Take the chicken and carefully place it into the pan," and the editor will shorten it to "pansear the chicken." The meaning is the same, but it's more concise. In a neural network, which is a vast web of interconnected nodes or neurons, pruning is the process of identifying and snipping away the connections that are the least important. During its training, the model has formed billions of these connections, each with a specific weight or importance, a parameter. It turns out that a significant fraction of these parameters have a value very close to zero. They contribute almost nothing to the final output. They are the neural equivalent of filler words, the ums and ahs of the network's thought process. The pruning process systematically finds these weak connections and removes them, creating a sparser network. You can often remove anywhere from 50 to 90% of the model's parameters without a significant drop in its performance for its designated tasks. It's like looking at the finished recipe for our Coke au vin and realizing it calls for a single incredibly expensive saffron thread, purely for a hint of color that no one will even notice. Pruning is the act of recognizing that this ingredient adds immense cost and complexity for negligible benefit, and simply snipping it from the recipe. The result is a model that is dramatically smaller in file size and faster to run. because there are simply fewer calculations to perform. It's a more streamlined, elegant, and efficient version of its former self. We've distilled the knowledge and pruned the excess. We have a lean, mean, intelligent machine. But there's one more crucial step, a final act of compression that is perhaps the most clever and counterintuitive of them all. This principle is called quantization. Let's go back to Chef Antoine's original recipes. Being a master of precision, his measurements are incredibly specific. His recipes might call for 12.735 grams of flour, or bake for exactly 21.45 minutes at 182.2 degrees Celsius. This level of precision is known in computing as using high-precision floating-point numbers. Each number is stored with a great deal of decimal detail, which takes up a lot of memory. It's like writing your recipe book on giant, glossy, high-resolution photo paper. It looks beautiful, but it's heavy and expensive. Quantization is the process of intelligently rounding these numbers off. It's about trading an imperceptible amount of precision for a massive gain in efficiency. Instead of 12.735 grams of flour, the quantized recipe might say 1 tablespoon. Instead of bake for 21.45 minutes, it will say bake for 20 minutes. For the vast majority of recipes, this tiny change in precision will have absolutely no noticeable effect on the final dish, but it makes the recipe itself much simpler and easier to read. In the world of AI models, quantization means converting those high-precision 32-bit floating-point numbers into much smaller, simpler 8-bit integers. An integer is a whole number with no decimal places. This is a radical simplification. You're effectively taking a number that can have over 4 billion possible values and forcing it into a system that has only 256 possible values. On the surface, this sounds like a terrible idea. It sounds like you'd be destroying the very nuance and detail that makes the model smart. But here is the surprising, almost magical truth. For most well-trained neural networks, it works beautifully. The models are incredibly resilient to this loss of precision. The essential patterns and knowledge are so deeply encoded in the relationships between the billions of parameters that rounding off the individual values doesn't break the system. The overall intelligence remains intact. The effect is staggering. By moving from 32-bit floats to 8-bit integers, you instantly reduce the size of the model by a factor of 4. It also makes the calculations much faster, because computers are fundamentally better and quicker at doing math with simple integers than with complex floating-point numbers. It's like discovering you can print your entire recipe book on lightweight, inexpensive paper, and the food still tastes just as delicious. So now we have the complete software story. We start with a giant teacher model. We use it to train a smaller student model through knowledge distillation. We then prune the unnecessary connections from that student model to make it leaner. And finally, we quantize its parameters, simplifying its mathematical language for maximum efficiency. Through this elegant multi-stage process of refinement and compression, we have successfully created our Micro LLM. We have taken the genius of Chef Antoine and transformed it into a perfect pocket-sized recipe book. The software is ready. But there is a final piece to this puzzle, a crucial, non-obvious element that is absolutely essential for the magic to happen on your phone. We've spent all this time crafting the perfect, efficient software, but that software needs a place to run. And for years, the hardware inside our phones was a major limiting factor. This brings us to the unseen giant of on-device AI. It's the silent partner, the unsung hero that makes this entire revolution possible. And it's not an algorithm or a piece of code. It's a piece of silicon. For most of computing history, the Central Processing Unit, or CPU, has been the undisputed brain of the computer. The CPU is a marvel of engineering, a general-purpose workhorse. It's designed to be a jack-of-all-trades, capable of handling everything from running your web browser and managing your email to calculating a spreadsheet and playing a game. To use our culinary analogy again, the CPU is the chef's all-purpose knife. It can chop, slice, dice, and mince. It's incredibly versatile and essential to the function of the kitchen. However, the specific type of mathematics that powers neural networks is highly specialized. It involves performing millions or even billions of relatively simple operations, mostly multiplying and adding numbers, over and over again on large groups of numbers called matrices. Asking a general-purpose CPU to do this is like asking your chef to whisk a gallon of egg whites to stiff peaks using only his all-purpose knife. He could, theoretically, do it, but it would be agonizingly slow, incredibly inefficient, and would tire him out completely. In the context of your phone, this translates to a sluggish user experience and a rapidly draining battery. For years, this was the bottleneck. The software ideas were there, but running them on the available hardware was just too painful. The breakthrough, the unseen giant, was the development of specialized hardware. Tech companies like Apple, Google, and Qualcomm began designing and building a dedicated chip, or a dedicated section of their main chip, with one and only one purpose: to run neural network calculations at lightning speed and with phenomenal energy efficiency. This is the Neural Processing Unit, or NPU. Apple calls theirs the Neural Engine. It is the secret weapon of modern mobile computing. The NPU is not a generalist. It is a specialist of the highest order. It is not the chef's knife. It is the custom-built, industrial-grade, electric stand mixer designed exclusively for whisking. It can perform that one specific task thousands of times faster and with a fraction of the energy that the general-purpose knife would require. It's a piece of silicon architected from the ground up to excel at the mathematical dance of matrix multiplications and linear algebra that AI models feast on. This is the beautiful, symbiotic handshake between hardware and software that makes on-device AI a reality. The elegantly distilled, pruned, and quantized Micro LLM is the hyper-efficient recipe. The NPU is the specialized appliance built to execute that recipe with flawless speed and efficiency. Without the optimized software, the NPU would have nothing efficient to run. And without the specialized NPU, even the most optimized software would still feel slow and clunky. The two evolve together, each enabling the other to reach new heights. This is the hidden hero inside your phone. It's the reason why Magic Eraser feels instant. It's the reason real-time transcription can keep up with your speech. It's the silent, powerful engine that takes the theoretical beauty of a Micro LLM and transforms it into a tangible, magical experience, all without ever having to reach out to the cloud. It's the ghost that truly lives inside the machine. So, let's retrace our journey. We began with a moment of everyday magic, a seemingly impossible feat of AI happening in a disconnected bubble. High above the earth, we questioned our common assumption that all-powerful intelligence must live in a distant cloud. We were faced with a paradox. How can something so smart be so small and self-contained? We opened the black box and discovered that the answer wasn't brute force, but elegance. The first principles of on-device AI are not about building bigger, but about building smarter. We learned that these Micro LLMs are not just dumbed-down or crudely chopped-up versions of their larger cousins. They are bespoke creations, carefully crafted through a process of apprenticeship. We found that this craft relies on a cascade of ingenious principles. Knowledge distillation, where a large teacher model imparts its nuanced wisdom to a smaller student. Pruning, the editorial act of snipping away the redundant, computationally expensive connections to make the model leaner and faster. And quantization, the counterintuitive trick of reducing mathematical precision to dramatically shrink the model's size without breaking its intelligence. We took a gargantuan, complex entity and, through these principles, distilled it down to its potent essence. And just when we thought we had the whole story, we uncovered the unseen giant, the silent partner in this technological dance, the specialized hardware. We discovered the neural engine, the NPU, a piece of silicon forged for a single purpose, to provide a stage where this optimized software could perform its magic with the speed and efficiency our modern experience demands. It's the perfect marriage of a refined algorithm and a purpose-built architecture. Understanding this journey from the cloud to the chip matters. It reveals a profound shift in the trajectory of artificial intelligence. For a time, it seemed the future was one of centralization, of a few colossal digital brains holding the world's knowledge, accessible only through a constant connection. But the rise of Micro LLMs points to a different, more personal, more distributed future. It's a future where intelligence is not just a service we rent, but a capability our own devices possess. It democratizes AI, making it more private, more responsive, and more deeply integrated into the fabric of our lives. It shows us that sometimes the most significant innovations don't come from making things bigger, but from the quiet, painstaking, and brilliant art of making them smaller. The next great leap in artificial intelligence might not be a thunderous boom from a distant server farm, but a silent, subtle spark of understanding happening right in the palm of your hand.
You've been listening to First Principles. Until next time, stay curious.